Welcome to clickmyproject.com. We will discuss about the product for memory footprint reduction for power efficient realization of 2D finite impulse response filters. Next we will see the abstract for the product. We have analyzed memory footprint and combinational complexity to arrive at a systematic design of strategy to derive area delay power efficient architecture for two-dimensional 2D filter impulse response FAR filter architecture. The DA based architecture consists of a adder tree architecture, and this architecture performs a carry save adder technique. The existing requires more than the time for the filtering architecture process. Our proposed work to modify the filter architecture using the fixed points LMS adaptive algorithm and to reduce the filtering time. We have analyzed the memory footprint and combination complexity. So we have presented a novel block based structure for a separable non-separable filter less than the memory footprint, memory sharing, memory and memory usage along with appropriate scheduling of a computation, and to design a storage architecture. The proposed structure involves a L times less storage per output and near L time less energy consumption for output compared with the existing structure. When the L input block size they involve L time more than arithmetical process than the best of corresponding existing architecture, and produce the L time more than throughput with less memory bandwidth compared to another methodology. We have also proposed a separate generic structure for separable and non-separable filtering bank and a unified filtering bank consisting a symmetric and general filter architecture technique. This architecture is mainly used to the two-dimensional digital filtering process and the DSP applications in our real-time processing architectures. Then we will see the flow diagram for the product, the input samples and the error samples to apply the delay unit architectures. The delay unit architecture is mainly based on the register element. The deflip register elements to use the delay adder process. Then the delay element result is applied to the partial border generation unit. The error bit samples is to create the error coefficient manner. Thus, the addition work to the error input bit samples using the partial border generation architecture. The partial border generation addition architectures mainly based on the carry select addition process. Then to apply the shift add architecture block. The partial border generation result is to pass the shift add architecture block. The shift add architecture block is used to the addition the partial border generation results in separate manner. This process is mainly used to the reduce the carry propagation time and to reduce the hardware complexity for the shift add architecture work. Then the shift add architecture result is applied to the delay and adder element. The delay and adder element mainly used for the store the results in register, then to apply the final output results. The final output results to get the delay and adder element. The delay element is mainly used for the deflip register element. The adder element is mainly focused by the LSB and MSB position for the shift add architecture result and to apply the delay and adder unit elements. The final output samples is mainly based on the synthesis and simulation results elements. The simulation results is mainly passed by the binary results element, and the synthesis report is mainly focused by the satisfy the parameter results for the in our architecture. And finally we see the output for the product. First of all, we open our processing folder, then we open the Xilinx ISC project. our program is developed in VHDL language, then we select the weighted update block to select the simulation work, then to select simulate behavioral model. We run the process for our processing result, then open the Xilinx ISM projects. The simulation behavioral model was completed successfully. Then create the ISM project list. Then we apply the binary input and to calculate the output weighted bits. Then apply the 16-bit data length for our project. Then add the error signal in coefficient manner. Then apply the clock pulse. We can create the programmable process. Just we close the simulation process. Next we go into this implementation work. The implementation work to create the view RTL schematic. Just we run the schematic diagram. The RTL schematic diagram is mainly used to create the RTL diagrammatic representation. Just we double click this diagrammatic representation is mainly used to what are the logical blocks is placed in our weighted filter architecture. Then the technology diagram is represents the what are the lookup table and input output buffers, then wire connections and flip-flop pairs to be applied by the our overall weighted filter architecture. Then we go to the design summary result, then the synthesis report. Just we generate the synthesis report for the weighted filter architecture. This architecture results is to calculate the area of the device utilization of weighted filter architecture, and finally we calculate the timing allocations for the latency and delay time calculation for our weighted filter architecture level.